In this lecture, we're going to learn how to think like a system architect, which is fundamentally different from thinking like a developer. When you're coding, you focus on making things work correctly. But when you're architecting, you focus on making things work at scale, reliably, and efficiently. Let me explain what I mean by this. A developer thinks about, how do I implement this feature? An architect thinks about, what happens when 1 million users use this feature simultaneously? A developer thinks about, how do I store this data? An architect thinks about, how much will it cost to store this data for 5 years? A developer thinks about, how do I make this code clean? An architect thinks about, how do I make this system maintainable by a team of 50 developers? See the difference? It's about thinking at a higher level, considering the bigger picture. Now, the first mental shift you need to make is stop thinking in terms of perfection and start thinking in terms of trade-offs. There's no perfect system. Every decision has the pros and cons. Your job as an architect is to understand these trade-offs and choose the right ones for your situation. For example, suppose you're designing a payment system. You have to choose between the consistency and the availability. If you choose the consistency, every transaction will be accurate. But the system might go down sometimes. If you choose the availability, the system will always be up, but you might occasionally have the inconsistent data. For a payment system, what would you choose? Obviously, the consistency, right? Because even a small error in the payments can cause huge problems. But for a social media feed, you might choose the availability. It's better to show a slightly outdated feed than to show nothing at all. This is architectural thinking, understanding the context and making the right trade-offs. The second mental shift is always think about the failure scenarios. The developers often think about the happy path, when everything works perfectly. The architects think about what happens when things go wrong. What if the database crashes? What if the network is slow? What if a data center goes offline? What if we get attacked by the hackers? For every component in your system, you should ask, what happens if this fails? And more importantly, how do we recover from that failure? Let's say you're designing an e-commerce website. The payment service goes down during the checkout. What should happen? One option is show an error and lose the sale. Another option is save the order and process the payment later when the service is back. Or maybe switch to a backup payment provider automatically. Each option has the different implications for the user experience, the revenue, and the system complexity. An architect needs to think through all these scenarios. The third mental shift is think in terms of components and interfaces, not the implementation details. When a developer sees a requirement like users should be able to upload photos, they immediately think about the upload function, the file validation, the storage logic. But an architect thinks differently. They see the components, an upload service, a storage service, an image processing service. And they think about how these components communicate, what happens if one is slow, and how to scale each one independently. This component-based thinking allows you to build the systems that are modular, scalable, and maintainable. You can replace one component without affecting the others, and you can scale the different parts based on their load. The fourth mental shift is always consider the cost implications. The developers often focus on the technical elegance, but the architects need to think about the budget. Every decision has a cost attached to it. Using the microservices sounds great, but it means more servers, more monitoring, more complexity. Is it worth the extra cost for your use case? Storing all the historical data forever sounds safe, but the storage costs add up quickly. Maybe you only need to keep the recent data readily available and archive the old data to the cheaper storage. Let me give you a real example. Suppose your application generates 1 terabyte of logs every month. Keeping them in a regular database might cost $500 per month. But moving them to the cold storage after a week might reduce the cost to $50. That's $450 saved every month. $5,400 per year. These are the calculations the architects need to make. The fifth mental shift is think about the entire life cycle, not just the launch. How will the system evolve over time? How will we add the new features? How will we migrate the data when we change the schema? How will we handle the technical debt? For instance, you're choosing a database. The MongoDB might be perfect for your current needs. The flexible schema, easy to start. But what happens 2 years later when you need the complex reporting? The MongoDB is not great for that, and you might need to migrate to a relational database. That migration could take months and cost the hundreds of thousands of dollars. An architect thinks about these future scenarios and makes the decisions accordingly. And finally, and this is crucial, architects think in terms of the patterns and the anti-patterns. Over the years, the industry has identified certain patterns that work well and others that cause the problems. An architect knows these patterns and applies them appropriately. For example, the single point of failure is an anti-pattern. If your entire system depends on one database and that database fails, everything stops working. The pattern to solve this is the redundancy. Having the backup databases, the load balancers, and the multiple servers. Yes, it costs more, but it prevents the catastrophic failures. Similarly, the tight coupling is an anti-pattern. If changing one service requires changing 5 other services, your system is tightly coupled. The pattern to solve this is the loose coupling. using the message queues, the API contracts, and the service boundaries. This makes the system more flexible and maintainable. So to summarize, thinking like an architect means thinking in the trade-offs instead of the perfection, considering the failure scenarios, thinking in the components and the interfaces, calculating the cost implications, planning for the entire life cycle, and recognizing the patterns and the anti-patterns. This mindset shift takes time to develop, but once you start thinking this way, you'll see the systems differently. You'll understand why certain decisions were made, and more importantly, you'll be able to make the better decisions yourself. All right, that's how to think like a system architect. In the next lecture, we're going to learn about the functional and the non-functional requirements.